Thank you very much. Well, I'd like to start by firstly thanking the organisers for a fantastic meeting. I came here 2 years ago and that was a great meeting, and I think this one's even better, so thanks very much. It's also lovely to be back at the Fields. I spent a sabbatical here back in 2015, and it's a wonderful organisation, and thanks for all the organisers. So I'm going to give a talk today which is mostly about non-smooth dynamics with a bit of machine learning. So this is obviously a conference on dynamical systems and machine learning. So I thought I'd talk about an area of dynamical systems that I'm very interested in and explore some links with machine learning. And I would like to say, if you want to learn more about the interaction between machine learning and non-smooth dynamics, Michael Muhlbach's talk was a great one yesterday, and he's written some wonderful papers in this area. I recommend you have a look at some of them. So this is joint work with my postdoc, Theo Devaney, and David Simpson over in New Zealand. Okay, so what's the idea of my talk? Well, as I said, this is a conference on dynamical systems, and what I want to do is try to explore ways by which we might understand and possibly control the dynamics of kind of machine learning type applications, such as neural nets and neural ODEs, by looking at them through the lens of a non-smooth dynamical system. Okay, so I'll explain a bit more what that means in the first half of the talk, and then in the second half, we'll have a look at some of the implications in machine learning. I should say, for me, this is just the start of what I imagine will be a bit of a journey. So a lot of what I'm going to say is quite speculative, and normally I wouldn't present these sort of results at a conference, but I know I'm amongst friends here, so do bear with me if you think some of this is very elementary. Okay, so where do we start? Let's start with dynamical systems. We're here at a dynamical systems meeting. So what is a dynamical system? Well, basically, it's some sort of evolutionary process, either a differential equation or a map. And what we're mostly familiar with, if you look at most of the textbooks on dynamical systems, are smooth dynamical systems. So you could have a flow, dx by dt is f of x, t, and some parameters theta, where the function f is a smooth function of its arguments. And much of the theory about dynamical systems makes that assumption. Similarly, you can have a map, which has the same property of being smooth. And many of the differential equations or flows that we've looked at this week have had that basic, very straightforward property. And then, of course, we know what to do. We know a lot about dynamical systems. They've been around for a long time. And what do? Well, typically, you might start them from some initial state x0, and you evolve forward in time, or thank you very much. Look at the service in this marvelous meeting. So you evolve forward in time or through iteration, and quite often, after not many iterations or not quite a short time, you evolve onto an omega limit set, and then you can study the dynamics by looking firstly at the omega limit set, and then how the omega limit set changes as you change your parameters, so typically through some sort of bifurcation. So what do we have? Well, the easiest omega limit set is you evolve into some sort of fixed point, and from a kind of machine learning point of view, that's very nice. You've got a nice thing you can then look at through a loss function, nice and straightforward. You can have periodic orbits, you can have quasi-periodic orbits, and of course you can have strange attractors. And as I said, varying the parameters allows us to move between these, and that's sort of, in one way, how you can control the behavior of these systems. And you can also, of course, analyze, for example, a feed-forward neural net as a dynamical system. This has been very much in fashion for some years now. Lots of people have worked on it. There's a very nice recent paper by P. Ashman and his co-workers looking at RNNs and echo state networks, but interpreting them in the context of excitable network attractors. So looking at attractors and how you can move from one to another typically through heteroclinic connections. So it's a very powerful approach. So let's have a look at some of the types of behavior we might have. We might have fixed points, which then evolve into each other through saddle nodes, and tipping points. We saw examples of this by Professor Lay's talk on the first day. We can have pitchfork bifurcations. We can have period doubling. We can have period doubling cascades. There's a classic one there, heteroclinic and homoclinic transitions. And so, as I said, by studying these, we can get insight into behavior dynamical systems, and thinking of machine learning as an example of that, it gives us an idea how a neural net might behave. And I say it's a very powerful approach. However, this is all made on this board the assumption that our dynamical systems are smooth. And I would argue that's not necessarily the best way to understand the sort of dynamical systems that we might want to look at in the context of machine learning. You might argue against that. I'd be very happy to talk about this. I think what might be slightly more relevant is the idea of non-smooth dynamical systems. Now, these are more recent things that people have studied. They, I think, were originally studied in the Russian literature, I might be wrong, then in the Eastern European, and then later in the Western literature. And I'm very pleased to have Ed Ott in the audience, who was one of the pioneers of this, and I'll talk a bit about his work presently. So what is a non-smooth dynamical system? Well, basically, it's the same as a smooth one, except that the right-hand side doesn't satisfy the conditions of smoothness, at least everywhere in the domain. And you can have flows and you can have maps. And I'm going to look at two types of non-smoothness, either genuinely non-smooth things, which are discontinuous or may have discontinuous derivatives, or what I would call smooth non-smooth things, which is where you have a non-smooth problem which is regularized in some way to be a bit smoother. So though they're technically smooth, morally they're non-smooth, and if you look at them from a distance, they look non-smooth. And many of the sort of things that we might look at in the context of machine learning have that property, as we shall see. Okay, so what sort of systems might we have? Well, one of the earliest examples, and quite well studied, are what are called Filippov flows. That's where you have a differential equation, dx by dt is f of x, where f of x takes different types of value in different sets. So a lot of problems in control theory are actually rather like this. A classic one might be the operation of a thermostat. The room gets heated at a certain level, and if the room gets too hot, the thermostat switches off the heating and we start to cool down. Okay, so that's a very classic example. So these sort of problems are quite common in control, which is to say why Michael Muhlbach's work is so relevant to this. And so you have smooth flows in sets, and then you have transitions between those sets, and you get changes. And you can have sliding, which means evolution along the set, if the function is discontinuous. So here's some examples of the sort of flows. On the left, we have a discontinuous map, where the flow might change its derivatives, but is continuous across the green line here is this discontinuity. In the middle, we have the classic Filippov flow where we get these discontinuities, and this is the sort of dynamics that you might get, where you might get sliding along the manifold coming in and coming off. I say many problems in control behave exactly like that. Or you can have systems where when you get to the manifold, some map happens and something else goes on. And a good example of that, I was hoping I'd have a ball here, but if I drop a ball on the ground and it bounces back up, we get a discontinuous change in velocity at the bounce. So that's a Filippov type system to do with flows, and we'll come on to some of these in a minute in the context of machine learning. Here's a different type of thing. These are maps. The same sort of idea. studied by Feigen. These are maps where the right-hand side, again, can change across a boundary. Now, see if the technology works. So you could have a function like this, so a map with a function looking like that, which is continuous, but has a discontinuous derivative at this point here. Or you could even have something which looks like that. Again, you have a jump there. So this is a classic Feigen map, which is continuous, but linearizable either side of the a manifold here where the non-smoothness is lost, and here where we have a discontinuity. If you have a look at this, that might look a bit familiar to you from a machine learning context, and we'll come back to why in a minute. Okay, so that's the kind of classic thing, again, we can study these as objects in dynamical systems land, they have many features which are very similar to smooth maps. Here's an example of a bifurcation diagram, which I shall motivate a bit later, of what is basically a non-smooth map, showing all the classic bifurcations one might expect: period doubling cascades, chaotic behavior, all of that sort of stuff. But also, there's a whole wealth of other types of structure that you can see as well. What we call discontinuity-induced bifurcations. So these are smooth bifurcations, but different types of transition which are associated with the non-smoothness of the system. So discontinuity-induced bifurcations, which I think one of the first papers, and I'm really pleased to refer to this, was by Ed and colleagues back in 1994. I wrote a book of them with my friends in Bristol, Arnie Nordmark and so on. So these are bifurcations which are associated with the lack of smoothness. So the border collision, which was defined by Ed in his paper, occurs where you might have a fixed point, either of a flow or a map, which, as you vary parameters, goes and if it might be fixed, it might be periodic orbit, but part of that goes and hits the manifold where the non-smoothness occurs. So as an intersection of the omega limit set with the boundary. Non-smooth folds typically occur when you get fixed points colliding on the boundary. Grazing, where you might have a flow where you get a tangential intersection with the boundary. So these are kind of points where the omega limit set interacts with the discontinuity. And then you can get kind of cascades of bifurcation. So everyone knows about period doubling. It's been around since Feigenbaum. Period doubling is 2, 4, 6, 8, blah, 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 and then you got something weird after the chaotic thing occurs. In non-smooth land, you get somewhat simpler things. You can get what we call period adding or period incrementing, where instead of multiplying by 2, you just add 1. And we'll have a look at some of those in a minute. And another feature of non-smooth dynamics is you can get robust chaos. Now, in the typical, in a Feigenbaum period doubling cascade to chaos, you don't have robust chaos. There aren't open intervals over which you get chaotic behavior. But in non-smooth dynamical systems, you can have open intervals of chaotic behavior. And that has enormous implications to studying the dynamics of them, both in their own right and in the various contexts they occur. Banerjee, I think, was one of the first people to see this, John Hogan at Bristol again, but other people have observed that. Okay, why might be bothered? So let's give some examples of this before I say why we're going to be bothered. Okay, so let's have a look at an example. So here's an example of what is generally called a map with a gap, which is very closely related to circle maps. So here is a map with a gap. You've got a linear feature, then a discontinuity, and then linear again, but you have a jump. We'll just take a very simple one, 0.8x plus b if x is 0, 0.8x plus b minus 1 if x is greater than 0. The 0.8 keeps things stable, And here is the map, linear there, there's the jump, there's non-linear. B here is our bifurcation or control parameter, whatever you want to call it. And what do you get? Well, on the left, here's an example of a type of flow. It's period 5, where the orbit is bouncing around between the two linear bits of the map. That's period 5. But if I look at an interval of the parameter value b, this control parameter, there's the period 5. If you see here, we've got a point where if I varied a parameter, that point could go towards the gap and then drops down. And what you get then is the creation of all this extra structure. And this is what we call period adding, because here's a period 3, there's a period 5, and between them is a period 8. So 3 plus 5 equals 8. Here's a period 2, 2 plus 5 is 7, there's a period 7. The period 2 actually creates a period infinity, periodic orbit, which is a bit weird, but anyway it does. And you get all this lovely structure in between the two, and there's some nice number theoretic fairy sequence type results here. And this sort of structure has been observed in circle maps. So that's the sort of bifurcation you might expect. And if you look over the whole range between 0 and 1, where you get stable behavior, we get this beautiful, beautiful structure unfolding like that. So that is this concept of period adding. If I look at a different type of map, here is a map where we're just taking nu1 and nu2, so we can vary the slopes, again, with the gap. So if one of ours is negative, we get a different type of behavior. This is called period incrementing, where we go 2, 3, 4, 5, 6, 7, up to infinity. And if I allow my values to be a bit bigger, so we get less dissipative behavior, we get this sort of chaotic behavior here, which is actually robust. We get these large intervals over which we get chaotic behavior. So that's kind of typical behavior of the maps that you have in non-smooth systems. That's a map. In a flow, you can get similarly complicated behavior. So here's an example of a flow where you have two fixed points indicated in red and green, discontinuity set so red and blue, discontinuity set in green. As I vary parameters, those 2 points can come together. And then when they come together, if you go a bit further on, you get a smooth behavior. And this is what we call a non-smooth fold, a non-smooth fold. Okay, so why might be interested in all this stuff? I mean, we've been looking at these as sort of theoretical objects for some time. Suddenly, in my opinion, they become relevant in the sort of context of machine learning that we're interested in this conference. So here are some applications. Well, the original studies of non-smooth systems largely came from mechanics. So looking at mechanical systems which are rattling, like gears, or you could have suspension systems on a car, or bouncing balls and all that sort of stuff. There's a French group, Broglie and his rather large group, have studied this a lot. Electronics, where you have switches, neuroscience, they come up there. My friend Anne Skeldon used these sort of models to understand sleep, and so on. My favorite application, which I do a lot of work on, is in climate, where non-smooth systems come up all over the place. And we heard again on Monday, Professor Lai was talking about detecting tipping points in climate models for AMOC, the overturning circulation. My own studies of that indicate that you can get non-smooth behavior with a non-smooth fold. Now, just to kind of refer to his talk, Professor Lai was talking about using machine learning to detect tipping points near smooth folds like that. And that's a good application of machine learning. There's lots of information. The problem with over here is you can't do that. And I'll try and give an example. If you look at this famous piece of chalk here, maybe I'll do it here, you might be able to see it. If I do machine learning on the dynamics of that, I won't learn very much. If I do it like that, I won't learn very much. If I do dynamics on that, I won't learn very much. And suddenly it falls over. And you can't predict that by observations before it falls over. And that is one of the problems with the AMOC. We might suddenly switch and not know in advance, which I find a bit worrying. Anyway, we're not here to study climate, although machine learning is very powerful in the study of climate, as we saw from Professor Ott's talk at the beginning of this conference. What I want to do, whether honestly or dishonestly, is to see how we might interpret machine learning in the sort of context of non-smooth dynamics. And here, it's all going to get very dodgy, and I apologize for that. This is, for me, as I say, the start of a journey. So why might non-smooth be relevant in machine learning? Well, basically, it's because we can view a machine learning architecture through the lens of a dynamical system. So let's have a look at, say, a basic feed-forward ResNet type architecture, which has this sort of form. So we're going through the layers. We have an input x0, we have an output xl, and at each layer we do the usual. We apply a linear map and activation function, and a linear map here to give the classic ResNet type architecture. And of course, what we want to do in machine learning is evolve this forward through many layers. We get to a final layer, we apply a loss function, and then we train the whole system dependent on the values of that loss function. Okay, so that's how machine learning essentially works in this relatively simple architecture. In principle, you could apply this to RNNs and more complex architectures as well. So if you have a deep neural net, so kind of the limit as L gets large, then it's not unreasonable to think that the value that XL takes will lie in some sort of omega limit set. So as you go through the layers, we get to some sort of recurrent behavior, and then that's what we can then attack with our loss function. I mean, it's not always the case, of course. It depends very much on the architecture and on L, but bear with me, that's the sort of things that I might be interested in doing. So we're going through the system, looking at the kind of dynamics as we go through and see what's happened. Now, why is machine learning different from any other thing? It's all due to, of course, the activation function sigma n. Okay, so let's have a look at some sigma n's. So if it's identity, well, not much happens, but the kind of first sigma n which was ever looked at goes back to the perceptron idea, which was this idea of a straight switch. A straight switch. So we're applying a Heaviside function to our right-hand side, and the Heaviside function is about as discontinuous a function as you could ever wish to have. Okay, so the dynamics with perceptron type function is like a map with a gap. It's one of these. It's exactly that. Okay. So we're getting that switch. If you go down to tanh, so tanh is, of course, very like that in shape. It is what I would call a smooth discontinuity. So if you have tanh with a large slope, then it's morally much more like a switch than it is like a smooth function. So when people say, oh, well, it's okay, everything's smooth, that's fine, but you've got very large derivatives. And I would argue to treat that derivative as infinity is actually makes some of the analysis easier. Here are various other ones, and here's, of course, the most commonly used activation function of all, ReLU. What's ReLU? Or parameterized ReLU over here. You can clearly see that the ReLU function has a discontinuous first derivative. We change slope either side of discontinuity manifold, so we're exactly where a Feigen map would put us. So the argument here then is that if you look at a kind of ResNet architecture with activation function, which is the two most, some of the more commonly used ones, such as ReLU, perceptron, sigma, heavy side, and tanh, they're all essentially evolutions of non-smooth type maps. Okay. So this gives us an insight as to how we might want to try to understand the internal dynamics of these sort of architectures. We can understand them to a certain extent by looking at iterations of these non-smooth things. So it's fearsomely complicated, of course, because X probably lives in a billion dimensions or something weird. We're applying all these activation linear maps and so on. But the non-smoothness and the fact that we get these transitions, to my mind, is one of the reasons we get such exciting behavior in neural nets and is partly behind the fact that they are so expressive. Okay. Non-smooth dynamics gives you a lot of expressivity. It also gives us, again, going back to Professor Muhlbach's talk, some notion that the control of these things is partly to do with controlling the way our omega limit sets intersect the various discontinuity manifolds. So that's that. And ReLU, as I say, is a particular case of this, where we activate on the positivity of the thing in the middle. And the switching manifold is basically any point where one of the terms of the inside here is 0. And is actually quite nice. The structure, you can go off and take it away and look at it. In one dimension, it's just a point, as I've indicated here. In 2 dimensions, it's 2 intersecting lines. And in n dimensions, the discontinuity manifold of a ReLU is n intersecting hyperplanes. And we'll have a look at that in a minute. So nice structures. And then as that gets evolved forward, so this manifold can get bent and twisted and so on, you can get really beautiful types of behavior. Okay, so another area you can get non-smoothness coming in is what we might variously call a neural ODE. Neural ODEs, in my mind, have a non-stable definition, but the definition I'm going to think of is where we have a differential equation where the right-hand side is given by some neural net, which we've trained in some way. What are we looking at here? Well, we're looking at a flow, and if that neural net has got ReLU activation or perceptron or whatever, the right-hand side, somewhere in its guts, is going to have discontinuous type of behavior somewhere through it. That's saying that if you're studying a neural ODE, they're not like ordinary ODEs. They are ODEs which have built into them some non-smoothness. And I say that that places a constraint on the possible dynamics, or maybe the opposite of constraint. Well, I'm not sure what that word is, but it opens up the dynamics to a great richness, which we can try to understand through the lens of non-smoothness and hopefully try and control as well. So this is kind of the point. I'd like to, at this point, say, well, I've completely solved it. I can give you lots of examples, and it's all wonderful. I'm not. I've not got to that point yet, but I'm going to try to give you some examples which at least motivates how I think we might try and tackle these sort of problems with this kind of way of thinking about things. So let's have a look at a case study. We're going to look at a feed-forward neural net, and I'm going to be incredibly simple here. I'm simply going to apply the same operation each time I go through. Of course, you never do that really, but the operation is, so we have a sort of ResNet type architecture. We have a linear thing here, and we'll have a heavy side here. So that would be a sort of perceptron going through. But of course, you don't ever use perceptron type things. We much prefer tanches. So let's smooth this out to a tanh. So C here being the control, and as I let C get larger and larger, then we have an approach to the Heaviside function. Okay. So this allows us to kind of interpret what I'm going to say in the context of the kind of normal type of activation that you might have. Well, let's have a look at the types of behavior. Well, basically, the omega limit set can be fixed point, it can be periodic, it can even be chaotic. Let's have a look at it. there we go, and it depends on how non-smooth we are. So if we have a very gentle tench, we just have a nice sort of thing here. That would be, this should be B along here. That would be lovely to train on. We'd have a very simple loss function, nice and easy, not very expressive, but easy. If you increase C by a little bit, we get the beginnings of the structure. See, what we have here is period 2, and that's born at a period 2 bifurcation here and here. So if we're close to that bifurcation point, we're going to be starting to generate more structure, and that's going to be relevant to any loss function. Take C a bit larger, we get the picture I put up earlier, and was on the front page of this talk. We're beginning to see more structure. There's period 2, there's period 3, period doubling cascade there, chaos here. C equals 50, so that's beginning to look more like a tench now. So we've got 2, 3, 1, 2, 3, 4. There's period 5, 1, 2, 3, 4, 5. Various bits of chaos in the middle. And taking it to the kind of the limit, well, I haven't taken it to the infinite limit, but we've taken it to 1,000. And we see exactly the picture I put up earlier, where we get these various types of omega limit set, and so on. So what's happening here, if we think of our, say, our neural net going forward, and we're trying to look at the omega limit set and apply a loss function to that, we might be applying it to something which is periodic or chaotic, or something simple in the case of C equals 1. So I put this up basically to illustrate how rich the behavior of these sort of things can be if you kind of interpret them in this kind of non-smooth way. So some conclusions. The high gradient of the tench, so C it doesn't have to be that big, 10, for example, leads naturally to chaotic behavior as you go through the network. And that means that the loss function might be kind of interesting to interpret in that case. And if we think of the parameters A, B, and C as the parameters that we might want to vary as we control the behavior, then we get a lot of kind of exotic behavior. And over here, back propagation would be perfect. It's nice and smooth, but we're going to get interesting structure going here as we go through these sort of border collision bifurcations. So the moral of this is we can get great expressivity out of these things developed by the non-smoothness, but back propagation isn't always going to help you, and I'll talk a bit about that in a minute. Okay. That's the kind of tenchy type thing. We've done a classification of this. If you're interested, you can classify the different types of behavior. Moving swiftly on. If you look at ReLU, you've got a little bit more smoothness in that ReLU gives you a continuous map with non-smooth derivatives. That's good, but it doesn't mean you don't get exotic behavior. So here's ReLU with parameters nu1, nu2, and mu. If I keep mu1 and mu2 fixed, you get this sort of behavior, by the way. This was observed in this seminal paper by Ed and company in '94. You can go from period 1, in this case, to period 4. Alternatively, if I vary nu2, we see this period adding, chaos, and all sorts of stuff here. And this is from a ReLU type map, Okay, and again, comments on that. So the dynamics that we see here, the key thing here is what we call symbolic dynamics, which is as you go through the network, whether the activation function acts to the left or the right of the discontinuity. You can do symbolic dynamics as to how that happens, which allows you to predict periodic cycles or robust chaotic behavior. And then you get your bifurcations when one of the symbols going left or right intersects with the boundary. And that can't be got from a back propagation analysis because you'd have to know where it was. And that leads to the expressivity. All of this works in higher dimensions, although it gets much more complicated. Some of the kind of behavior is not unlike that which Ashwin and his group found for the ESNs. Okay, so it's kind of a fascinating story that we're beginning to see because of this. So that is these sort of maps, and then again you can classify, these are the symbol sequences, the different sort of things that you get. So we've got a degree of understanding of what you might get. Let's have a look now at flows, so neural ODEs in the context of things where on the left we have dx by dt, on the right we have the output of what might be some sort of dynamical, some sort of neural architecture. So here is, you might not recognize it, but this is a model for the Ice Ages, which I've extracted by doing some sort of machine learning, looking at data. Believe me if you believe me. Actually, it's not that bad. It gives quite good answers, predictability for the Ice Ages. But here we have a sort of dx by dt, again has a ResNet type structure, Lx plus b, and then the Heaviside activation. And I can interpret that in a fairly simple way as Lx plus either b plus or b minus, dependent upon whether my C transpose x plus d is either positive or negative. So that's a sort of neural ODE type structure with Heaviside activation. Let's have a look at the sort of dynamics we can get from this. So here's the dynamics. The F is the thing inside the Heaviside. We get a smooth evolution. There's my manifold. We go down that way. You can get fixed points of this, and you get two types of fixed point, what we call physical, which are ones which occur at the same time as the manifold structure is right, or virtual ones. And you can study the structure of this as you change the parameters, as you go from, as these fixed points intersect the boundaries in these border collision bifurcations. And to cut a long story short, you can find an evolution in these sort of systems from behavior which has fixed points and behavior which is periodic. And what's interesting is that the neural architecture has managed to learn through this the periodic behavior that you see in the Earth's climate associated with glacial changes. And this model is actually quite reasonable in reproducing what you see. And yeah, here's a sort of bifurcation that you get as you vary parameters. You can have this evolution from a fixed point to periodic behavior and then back to a fixed point here. And if you replace the Heaviside by a Tanch, so it looks more like the activation you get in a more realistic machine learning architecture, you go from fixed point through a bifurcation. In climate world, this is the variation between glacial and interglacial type behavior, and then back to a fixed point again as we vary parameters. And I want to kind of finish this talk by talking a bit about the kind of the dynamics that you might get with a neural ODE where you get a sort of ReLU type structure. So here we have a sort of typical kind of ReLU type structure. By the way, this is very simple. It's just a single layer. Multiple layer is much more complicated, but at least with single layer I can do some analysis. So here is a neural ODE, dx by dt, with some sort of ReLU architecture here. And again, I've indicated with the cross the sort of behavior, thus the sort of discontinuity manifold that you get where A2x plus B2 transitions through the various kind of activation bits of the ReLU. So that's the kind of structure. Typically this has fixed points, and if we look at the fixed points, that might be a fixed point. As I change parameters, my training parameters, so the fixed point will change smoothly, my loss function will change smoothly, until it hits the activation bit of the ReLU, and then it will change. It will go off in some different direction because we've crossed over. Back propagation will work fine here and here, but over here, we're going to have trouble. This is very, very similar to the picture that Professor Morbach put up yesterday in a somewhat different context, but it's a similar kind of thing, that we get changes as we go through. So what do? Well, we can actually do something which is nice. Here is the kind of intersecting hyperplanes that are associated with the typical ReLU function. As I change things, I'm unlikely to intersect more than one hyperplane at a time. So it's a high codimension occurrence if I do. So typically, I intersect one hyperplane as I change things. So I only need to study the transition across one hyperplane. So suppose that hyperplane is C transpose X equals D. Then either side, ReLU is linear. And so the normal form, as I go across, looks like this. We get linear plus mu. I've put C trans. I've set D to 0 without loss of generality. And this is the other side. So this is kind of a normal form when back propagation is breaking down at that transition. And this has been studied. Here are two of the people that have studied it. You can classify. So we can have fixed point going to fixed points. That'll be relatively straightforward. You can have fixed points annihilating each other. You can have fixed points going to limit cycles or fixed points going to chaos. So we can actually classify these things. And I would loosely argue that this helps us understand and control these things as we go through. I'm nearly done. So here's two examples. Here's an example of that ReLU kind of structure with these two matrices here, not chosen completely randomly. And what happens here is there's a fixed point as I vary the parameter b. It hits x equals 0, which is the manifold where it loses discontinuity, and throws off a limit cycle in the process. And that's the bifurcation diagram. Oh, that should be b, not mu, I apologize. So the fixed point goes to a limit cycle here. Slightly more interestingly, if we go up a dimension, then fixed point here hits the manifold and throws off a chaotic orbit. So as I go through, back propagation will be perfectly good here, and suddenly we're into chaos land. Here's the sort of bifurcation diagram that you might get in that case. So again, here, relatively easy. Here, oh my goodness, so all sorts of things happening. Right, to finish, we've demonstrated that typical activation functions lead to complex behavior in feed-forward neural nets and neural ODEs, and that, I would argue, is part of the power of these things. It's part of the expressivity. And we can actually do something about how one classifies these sort of things. Of course, you're all shouting at me, your architecture is a trivial, do a proper job of it. And yes, I agree, and that's what we want to do next, is understand how this works for much more realistic, higher dimensional machine learning architectures. And also how understanding these sort of structures might improve training and control. Having been to Michael's talk yesterday, I got to go off and read all his papers to see how they've done it in the context of differential inclusion. So thanks for your talk. That's basically it. And just to put up a few references as we go forward and say thank you very much.